structure. You have different type for manipulating things. After, you can add hydrogen like this. What to say more? Okay. PDB, rotate structure, etc. The hydrogen, optimizations. So you go to simulations, simulators, option. So we'll optimize the proteins like this. Okay, it's done. Yesterday I put molecular dynamics. If you want to do the same, you can just put on. It is not in the protocol, but the same. You can see the dynamics. And here the protein is relaxing.
Sao đang thua ông ấy dạ?
Okay, so here it's the basic manipulations. So okay, we have also another structure, 1-packs. Okay, you can do it. Okay, so I will let you, I think, an half an hour to play with that. So I am here, I am connected. Okay, I will just shut down microphone. Okay, but I am here at your disposition if you have any problems. Okay, so if you don't succeed to install Yathara, just say me it now, or just, well, I am here, so if you have some problems, you can say me, well, I have a problem, how do you do this, etc. Okay. I know that practical session is better when the teacher is in the room. But well, with COVID, it's not so easy, and the border of Vietnam is closed for the moment. So you can work. So if you want to do it, no problem. Okay, but please do it after the practical session. Do it alone. For example, this night when you want to go to sleep, you put your sequence, put it on the SRI, push the button, keep the computer on, and go to sleep. And during your time and during your night, the computer will work. So it's the first option. The second option to go faster is to use web services. So web services is services with computer, with a server aboard, and we have one. We suggest to use this or web server in France, but if you want to use other server in Switzerland or in the US, no problems. I can send you address. Okay, so you take your sequence there, here. So copy. I also I switch to section 2. Yeah, so I go to Geno 3D. So you are here. Okay. You put your sequence. My prot. And you pass the sequence. So here, okay, is Geno 3D database in non-redundant protein sequence. So Geno 3D is a model biomology, so we'll make, in fact, this sequence is no structure for it. Oh, can I count this as branch? I have to add all atom, but I want just to show, okay. Just I answer the questions before. Okay, the best options, well, view, hide atoms, hide hydrogens. Okay. Well, if you want, okay, so I my hydrogen from this structure, and I'm checking the best options. Maybe this one is good. Okay, it works. So you can do it like that. Show. Oh, yeah. So at the start you are like this. Okay, for the people from the people who say, how could I count SS bridge? Okay, so you have the structure like this. Just bigger. Like this. It arrived. Yeah. If you click on one seren, you have the inside what is in seren. It's mol A. If you click on mol A, you have all amino acids there. Okay. The idea is like to see cysteine, you have two options. The first option is hide hydrogens. So view, hide atom, hydrogens. And here, in fact, steel sulfide bridge is there. You have one here, and one here. Okay, this is your option. The other option is to hide all residues. So just to keep yes, here it's visible. So you just keep cysteines, yes, and the other one, no. So you can do it like that. And when you see cysteine, you say yes. Here, well, I miss one. Yeah, okay, should be okay. And this, you are here. Okay, you can see one here, one here, and one here. Okay, so this is your free hydrogen bonds. Sorry, your free SS bond, disulfide bridge. That's okay for this? Okay. So start again. Oh, analysis structure. But for example, for this structure, you can say, well, here I have two alpha helixes, one here and one here. Okay. Two split here and here. Well, we can start by the protein is only one chain, chain A. Okay, this chain A is stabilized by three SS bonds, and the structure have two small helices starting from well here. Okay, so here it's number 16, 67 to oh sorry, well starting again. I miss the right number. Starting from proline 5, you can see here. Okay, to well, maybe this one it will be better. From leucine 18, and another alpha helix there, starting in there. Alanine 25 to glycine 31. Okay, and two beta sheet, two small beta sheet, one is there. Yeah, starting at isoleucine 33 to to 36, and the other one is starting at it's starting at well, in fact, it is the first one. Starting at residue 4, cysteine 4, and it's 1 to 4. After it's one helix, another helix, and finished by another sheet. And that's it. Okay. Okay, so for the modeling of homology, you have a sequence here, it's by proteins. So you have database of non-redundant sequence protein. Just click on submit. It will start working. So here it will give the different fold find in the database. It will work. Okay, so here it's a psi blast, so it's a blast on the sequence with a structure. The ID, which is the most important things here, it's the identity of sequences. So you have 95% or 97% of 95%. Yeah, so, well, all length is covered because my protein has 46 residue, so starting 1 to 46. So, well, what I will take the first one because the homology is higher, so I will take this one and say select template. So it will align sequences. Okay, so here is my sequences, will be aligned with these proteins. I give here my email address. Here in the first step, don't forget to choose 5. 5 model is clearly enough. Okay, and you put your email without error. You click on launch the jobs. The computer will work for you and receive in your email the link to download the best structure. Okay, and that's it. And you have your models. So I give you some time to do that. I am here if you have any question. No problem with the chat. Okay, I give you I give you 1 hour to finish the first part and send your sequence. And after I will I will stay connected to answer to your question. I will just shut down the camera. And if you have any questions, so don't bother to ask me. I am here, and after we'll see for docking simulations. Okay, good work. Then when you take your models, well, I don't put it. Well, okay, so the first section, you analyze the structure. So for people who ask me how to analyze this, in just describing your structure. So you have here your proteins, and you will analyze it. So if you analyze it, you see that in only one chain. It's easy to see one chain. You can see here, it's one chain. And after, basically, you describe what you are viewing. So here, yeah, like this, it will be better. So the chain start here. You make alpha helix there, a loop, alpha helix, a sheet, and, well, nothing random at the end. So your analysis just is to say, well, I have one chain, it makes 2 alpha helix and 2 antiparallel beta sheets. And to have where it starts and where it finished, you can see here, you just click on it, or you also go there and click there. Okay, 1. 2, well, it's not working like this. Okay, never mind. F8, yeah. Okay, this you can click on atom. When you click on one atom, the athlon BIMP, and you are here. You have here information about these atoms. So you can see here, it's here residue threonine 1. So it's the first one, and if we want to finish the beta sheet part, it's finished there. So I just click there, and in cysteine 4 is finished. Okay, so free residue in beta sheet. After you can see there are an alpha helix. So an alpha helix, well, roughly it starts there and finish there. And here, if you are here, you can see also sequences. Okay, so you can check also like this. You go on the mouse on the bottom of the screen, the sequence appear, and you can do also like this. So yeah, valine maybe isoleucine, yes. So the alpha helix will start in 7, finish in 16 or 17 or 18. Well, 18 is better. After the other alpha helix will start in 23 and finish not there. Yes, this is better. This is not too bad. Okay, so you can check. It's finished on 31. After, no. After I want the beta sheet there. Beta sheet start there. So you can click there and you have information there, or you can click in the bottom of screen to have also the same information as you want. Okay, with this software, there are plenty of things to do, so no problems. Okay, and you describe your structure like this. Just check if it's finished, started, and it's ended. Okay, so you received 2 mails. The first mail was started. Okay, so it started, and the other one was ended. When you have ended, you click to ended. You have a link, and you have your model there. And you want now to say, what is my best model between these 5? So you have a complete model analysis there, okay? You can click on report, and here it is your report. So you have the energy of your models. So model 1 is minus 1000, etc. Okay, so all energy is negative, which is logical, but energy is not enough to check which is the best model. In fact, the best model, it's very interesting. In fact, if you use a Ramachandran plot, you have here your plot. So you have 2 types of, well, it's the same, in fact. You will have here. Here it's really interesting. Why? Maybe I can put higher. I will not succeed. Here it is your plot. So Ramachandran is a professor which analyzed some decades ago all angles in protein known. A protein which has a structure, and made a statistical analysis of what he found. And so you have 2 angles, phi and psi, for each residue, and you have in your models 46 residue. So you must have 46 black dot. Okay, hold on. For 1 residue, 1 dot. Okay, and for 1 residue, the computer will measure the angle of psi and phi and report it and put it on the Ramachandran map. If your protein is correct, all your dots should be in a red area. Red area means allowed area. If it is not in in a allowed area, you have also, well, possible area. And it's a dark yellow. And you have also white, light yellow. Light yellow, it's allowed. It's, well, really, really possible. Generously possible. And if it is white, there are some problems. So here you can see that the model one, I have 1 point in dark yellow. Here I have a few points there, but no point in white. So not so bad. You have also here statistic. Core is a red part. Allowed is a dark yellow. Generous is a light yellow. And disallowed is a white. Okay? So you can see that model 1, model 2, model 3, model 4, and model 5 are all 0% in disallow. So basically, roughly, all models are not so bad. Here you can see there that generously it's the same things. Okay? And in fact, core and allowed, it's the same. Oh, not totally the same. This one is lowest. Yeah, okay. This one is the highest. So the best idea is to have a lowest percentage in allowed, a lowest in generously, and nothing in disallowed. So all models have 0% in disallowed. So all models are good. But it takes the best one. So the best one, generously 0% everywhere. So perfect too. Here it is the highest. After, so I have one highest. So model 5 is not a good one. Model 4, model 3, and model 1 is the same, but model 2 here is clearly the best. Why? Because I have more percentage here on core, okay, and this is the lowest. So model 2 is not so bad. In terms of energy, it was not the lowest, but is clearly the second lowest. Okay, so yes, I prefer model 2. So for me, I check for model 2, it's the best one. So I can go back and say I want model 2. Okay, so you can register, you can save your files on your computers. And after you go to Yasara. And here, if you want to see your result, you will load your PDB files. So I put it in the cloud. This is my proteins. So edit, add hydrogen to all. And here it's my modeled proteins. Okay, biomology. So I have a sequence identified by different researchers. This structure was never resolved. I have the sequence. I want the sequence. I want to have models. So I go to a model biomology. I think I could make the model biomology, and I use a template with 97% of identity. So the model will clearly excellent, no problems. I made the model biomology, and now I have my proteins, so I can work with it. And that's it. Okay? So, this is part 2. Part 3. So part 3 is the most complicated, and well, this is very challenging. Okay, so if you don't finish today, no problems. You can send me a question by mail. I will help you by mail if it is too long. Okay, no problems. So you have, so for people with Mac versions, you have to, well, you can do two things. If you want to draw the molecules, I don't have the ICD sketcher for Mac. It don't exist, but there are plenty of chemical sketcher. So you can find another program to sketch a molecule, like Marvin or plenty of programs. Okay, so just take any program to draw your molecules and to save it in MDL4, mol file. Okay. If you doesn't want to draw the molecule, I show you a tips, a trick. Okay, you are here, drug bank. Drug bank is a database with all molecules on it. Okay, all molecules with already drugs. So here I want amoxicillin. I find here amoxicillin. Then there are the drug. Here it's a molecule. So if I want, so you can see the molecule in 2D, you can see the molecule also in 3D. Maybe it works. 3D. And you can here you can save your molecule in mol file. Here. So this is the mol files. Well, don't be afraid. You have just to save the. Here you go and to say save. Yeah, just like this. Okay, enregistrer. Download. DB mol. Also, I can put the real name, Amox. Okay, and if I go back to Yasara, new, yeah, I can put. So here I load over file formats. It's MDL4 and MDL mol. So you have just to check where is it, MDL mol. Go to download. Where is download? Download. And you'll find your files. I have plenty of files. Here is the files. Okay. And you have your molecule. Edit, view, still atoms, sticks. Oh, why? Here. Okay. Edit, add hydrogen to all. Yeah, and after option, choose energy minimizations. And is parameterize atoms, and it should work. It will work. And it works. Yes. And I have my molecules. Okay. So to make the docking simulations, you need to have 3 files. You need to have the receptors and the 2 molecules. Okay, you have amoxicillin and cefixime. So first step, 2 options. You could go to drug banks and download the structure. Okay, put in Yasara, minimize it, and save it. First options. I call it trick option. Other options, you take the ACD chem sketch, you draw the molecules, you save the molecule, you put it in Yasara, you minimize, and you save your molecule. So at the end, you must have two files in MOL2 formats. Okay, so here, yes, in MOL2 format, here, save it. Okay, save the structure in Sibyl MOL2 format. Okay, so you must have at the end two files. The one ligand, the amoxicillin ligand, and the fixing ligand. Okay. It is okay? I suppose. Well, let's start. And if you have any problem, the chat is open. And I will answer, even show you how to do more precisely. Okay, if you have precise questions. I stay here, no problem.